Let us look at the recursive binary search algorithm. We will also analyze its time complexity. The binary search is used to determine whether an element X is present in an array. A very important point to remember is that for binary search to work, the elements in the array must be in sorted order. This is because binary search follows divide and conquer approach. The divide and conquer approach divides the problem into subproblems and sub-subproblems until the problem is small and can easily be solved. Let us call this algorithm as R-bin search for recursive binary search. This algorithm takes 4 parameters. The first parameter is array A. The second parameter is the left index. The third parameter is the right index. And the fourth parameter is the element we are trying to search, that is the key. Now, in the first part of this algorithm, we will handle the case when the problem is small and can easily be solved. That is the case where there is only a single element in the array or the subarray. If there is only one element in the array, then the problem is small, and we can compare the key with a single element of the subarray or the array. So, we will have the if statement with the condition as left index equal to right index or L equal to R. If left index is equal to the right index, that means there is only a single element in the subarray or the array. Therefore, within this if statement, we will check if the key is equal to the element at the left index, that is A of L. If this is true, we found the key and we will return the left index. Here, we can compare the key with the element at the left index or the element at the right index, because both the left and the right index are the same. Otherwise, we have a single element in the subarray and that is not equal to the key. So we will have else return 0, that is, the key is not found. So when the left index is equal to the right index, then the problem is small and we have the solution, that is, the key is found or key is not found. This if statement of L equal to R will also be the base condition for the recursive calls. Now, remember, we have not yet divided the array into subarrays. Now, when the problem is large, that is, when there are more than one element in an array, then we will apply the divide and conquer approach. So, we will have the else block. Within the else block, according to the divide and conquer approach, if the problem is large, we have to divide the problem into smaller subproblems. In binary search, we divide the large array into 2 smaller subarrays. To do this, we will have to compute the mid index. That is, mid is equal to left index plus right index divided by 2. Then we will check if the key is equal to the element at the mid index using if key equal to A of mid. If this is true, we found the key and we will return the mid index. If the key is not found at the mid index, then the key may be in the left subarray or the right subarray. So when the key is smaller than the element at the mid index, then we will have else if statement with the condition key less than A of mid. If this is true, then we will perform the binary search recursively on the left subarray. So we will have the statement return and recursively call the binary search, that is R-bin search algorithm, passing the array A as the first argument, the second argument as L, that is the left index, and instead of right index, we will pass mid minus 1 index as the third argument, since we have to perform binary search on the left subarray, and we will pass the fourth argument as the key. Otherwise, when the key is greater than the element at the mid index, then we will have the else statement and perform binary search recursively on the right subarray. So we will have the statement return and recursively call the binary search, that is R-bin search, passing the array A as the first argument, and instead of the left index, we will pass mid plus 1 index as the second argument, since we have to perform binary search on the right subarray, and we will pass the third argument as the right index. and we will pass the fourth argument as the key. So this is the recursive binary search algorithm using divide and conquer approach, where the if statement L equal to R is the small problem for which we can easily compute the solution, since when L equal to R, the subarray will have only one element. Otherwise, the problem is large, and we have the else block where we divide the array into subarrays and recursively call the binary search algorithm till we find the key or the key is not found. Now let us analyze this recursive binary search algorithm. Since this is a recursive algorithm, the time complexity of recursive algorithms are computed using recurrence relations. Let us look at the recurrence relation for this algorithm. Let us assume that the recursive binary search algorithm takes t of n time to compute, where t is the function that takes size of the input as n. The if block where L equal to R is the solution for the small problem, and all the statements within this if block are primitive statements. Therefore, the statements within the if block will take unit time to compute. So, the recurrence relation t of n can be written as t of n is 1, that is, it takes unit time to compute if n equal to 1. Here we have n equal to 1 because in the algorithm, if L equal to R, that means there is only one element in the subarray, and one element means n equal to 1. Therefore, t of n is 1 when n is 1. Then, when the problem is large, we have the statements in the else block, where the mid statement is a primitive statement, as well as if key equal to a of mid is also a primitive statement and will take unit time to return the mid index if the condition is true. Then we have recursive calls to our bin search algorithm depending upon the key. This is the very important part. If the key is less than the mid element, then we make a recursive call on the left half, or if the key is greater than the mid element, we make a recursive call on the right half. So each time the recursive call is made, it's only on the half of n. And since the time taken by our bin search algorithm is t of n, then these statements will be taking t of n by 2 time to compute. Therefore, if the problem is large, that is, if n is greater than 1, then the time taken is t of n by 2 for either recursive calls plus 1 for computing the mid value, which takes a unit of time. So this is our recurrence relation for the recursive binary search algorithm. Now, we will use the substitution method to solve this recurrence relation to compute the time complexity. Using the substitution method, we have to repeatedly make substitutions for each occurrence of the function t on the right-hand side until all such occurrences disappear. So let us consider the first occurrence of t of n equal to t of n by 2 plus 1 as the first equation. Then what will be the second occurrence t of n by 2? T of n by 2 will be, we just have to substitute n by 2 in place of n. So we will have t of n by 2 equal to t of n by 2 in place of n divided by 2 and then plus 1 from the original expression, which is equal to t of n by 4 plus 1. So this becomes our second equation. In the same way, what will be the next occurrence? T of n by 4. T of n by 4 will be, we just have to substitute n by 4 in place of n. So we will have t of n by 4 is equal to t of n by 4 in place of n divided by 2 and then plus 1 from the original expression, which is equal to t of n by 8 plus 1. So this becomes our third equation. Similarly, what will be the next occurrence? T of n by 8. T of n by 8 will be, we just have to substitute n by 8 in place of n. So we will have t of n by 8 equal to t of n by 8 in place of n divided by 2, then plus 1 from the original expression, which is equal to t of n by 16 plus 1. So this becomes our fourth equation. Now we have t of n and we have found t of n by 2 as well as we have found t of n by 4 and t of n by 8. So we have these four equations. Now let us try to substitute them in the recurrence relation. We will start with t of n, which is equal to t of n by 2 plus 1. Then we can also rewrite t of n as, instead of t of n by 2, we can substitute the second equation, that is t of n by 4 plus 1. So we can also say that t of n is equal to t of n by 4 plus 1 plus 1. Then instead of t of n by 4, we can substitute with the third equation, that is t of n by 4 is equal to t of n by 8 plus 1. So we can also say that t of n is equal to t of n by 8 plus 1 plus 1 and plus 1. Then instead of t of n by 8, we can substitute the fourth equation. That is, t of n by 8 is equal to t of n by 16 plus 1. So we can also say that t of n is equal to t of n by 16 plus 1 plus 1 plus 1 and plus 1. So here we have substituted t of n by 2, then we have substituted t of n by 4, then we have substituted t of n by 8. But how long should we continue? Let's say that we continue the substitution for I times. So when I is 1, we have the first equation, which is t of n by 2 plus 1, and can be written as t of n by 2 power 1 plus 1. Then for the second substitution, that is I equal to 2, we have t of n by 4 plus 1 plus 1, which can be written as t of n by, instead of 4, we can write it as 2 power 2, and plus 1 can be written as 2. Then for the third substitution, that is I equal to 3, we can have t of n by 8, which can be written as t of n by, instead of 8, we can write it as 2 power 3, and plus 1 can be written as 3. Then for the fourth substitution, that is I equal to 4, we can have t of n by 16, which can be written as t of n by, instead of 16, we can write it as 2 power 4, and plus 1 can be written as 4. And so on for the ith substitution. We can write the equation as t of n by 2 power I plus I. Now, using the successive substitutions, we have substituted the function t repeatedly for I times until the expression reduces to smallest value. That is, in this case, smallest value of n equal to 1. So now we can say that n by 2 power I has eventually reached 1, for which we have the solution, that is t of n is 1 when n is 1, which is t of 1 equal to 1. So when n by 2 power I is 1, we can write it as n equal to 2 power I, which can also be written as I equal to log n base 2. So t of n will be equal to, instead of t of n by 2 power I, we can write it as t of 1, since we have reduced the expression to the smallest value, and instead of I, we can write it as log n. Now t of 1 is 1, that is when n is 1, plus log n. Therefore, the recurrence relation is reduced to a polynomial, t of n equal to 1 plus log n, using the substitution method. And now we can say that t of n will be O of, or order of log n. Therefore, the recursive binary search algorithm will be taking O of log n as the time complexity. So this is the recursive binary search algorithm and its time complexity.